Hello. I'm going over today the Avogadro's law, process, and impact. The modern process today in Avogadro's hypothesis is confirmed through advanced tools like spectroscopy, electron microscopy, and gas laws, tested under precise lab conditions. Avogadro's constant is measured using X-ray crystallography and the silicon sphere method. That's 3.1 and 3.2 is differences in approach. Unlike Avogadro's theoretical reasoning, modern science relies on direct experimental evidence, precise instruments, and standardized international units, like the mole being defined by exact particle count. And then 3.3 and 3.4. The modern benefit. Avogadro's number is essential in chemistry, physics, and nanotechnology. It enables accurate chemical calculations, helping in determining molecular structures, and supports industries from pharmaceuticals to materials science. And that's 3.3. Now we're going to 3.4, future expectations. As technology advances, measurements of fundamental constants will become even more precise. Ongoing research in quantum chemistry and nanoscience continues to rely on Avogadro's principles to explore atomic scale behavior and develop new materials.
Avogadro's number, which is approximately 6.022 times 10 to the 23rd, is the number of particles in 1 mole of a substance. It serves as a bridge between the atomic scale and the macroscopic scale, which allows scientists to count particles by weighing them. Named after Amadeo Avogadro, it's a fundamental constant in chemistry used to relate the mass of substances to the number of constituent particles. A few of the relevant fields to Avogadro's number are chemistry, biology, physics, pharmacology, and material science. Chemistry because it's used to calculate the number of atoms, molecules, or ions in a given amount of substance. Chemistry is essential for balancing chemical equations and determining molar masses. Biology because it helps quantify molecules in biochemical reactions, such as enzymes, DNA, or proteins in given sample. Physics is important in atomic and molecular physics for understanding particle behavior and statistical mechanics. Physics is used in calculations involving the ideal gas law and Avogadro's law. Pharmacology assists in determining the number of drug molecules in a given dose, especially in the molecular scale. And last but not least, material science. It's applied when analyzing atomic arrangements in crystals or the composition of materials at the atomic level. A few of the relevant scientists for Avogadro's number include Avogadro himself, to the far left. We have Johann Joseph, I'm not sure how to say his last name, I'm gonna butcher it, but bear with me. Loschmidt. We have Ludwig Boltzmann, and last but not least, Jean Perrin. So let's start with Avogadro himself. He was an Italian physicist who first proposed that the equal volumes of gases at the same temperature and pressure contain the same number of molecules. Although he didn't determine the actual number, his idea laid the foundation for the concept of the mole and particle counting, hence the name Avogadro's number. Next we have Ludwig Boltzmann. He was an Austrian physicist who related the gas constant RR to the Boltzmann constant KK, and Avogadro's number through thermodynamics and statistical mechanics. Next we have Johann Joseph, and the last name I cannot say. He was an Austrian scientist who was the first to estimate the number of particles in a given volume of gas, known as the Loschmidt constant. His work indirectly contributed to calculating Avogadro's number. And last but not least, we have Jean Perrin. He was a French physicist who experimentally confirmed Avogadro's number using the Brownian motion and received the Nobel Peace Prize in Physics in 1926. His work helped solidify the atomic theory and provided strong evidence for the existence of atoms and molecules. So let's get into the experimental process and impact of Avogadro's number. Avogadro proposed that equal volumes of gases at the same temperature and pressure contain an equal number of molecules. This idea formed the basis for Avogadro's law, even though, as we recall, he did not create it himself. He just laid the foundation. He heavily relied on reasoning from existing gas laws. His hypothesis was initially met with skepticism due to lack of experimental evidence and the limited technology available at that time to measure molecular quantities. As you see, I have the timeline down here, 1811 to 1856. Many did not recognize the importance of his idea until later, which is why it wasn't developed by him. Next, the experimental process and impact of Avogadro's number. His main motivation was that he was driven by a desire to understand the behavior of gases and unify various gas laws. Avogadro aimed to explain why gases behave in predictable ways and to propose a more comprehensive theory. His work led to the development of the mold conception, revolutionizing chemistry and allowing for more accurate measurements of atomic and molecular masses. It also contributed to the creation of ideal gas laws and paved the way for the determination of Avogadro's constant.
4.1. Relevance of the question to the topic explained. The example question we chose is relevant to this topic because it uses Avogadro's number to determine how many molecules of nitrogen are in 3.0 moles of nitrogen gas. Avogadro's number represents how many particles are in 1 mole. Therefore, we were able to use his number to determine how many particles were in 3 moles of nitrogen gas. 4.2. The benefits of understanding the question given. By creating and solving a problem specific to a topic you are learning about, you can further understand the topic in a real-life scenario. In any case, physically working out a problem and getting it correct gives you the satisfaction of truly comprehending what you are learning rather than just reading it. 4.3. The process of writing the question outlined. We chose this question because nitrogen gas is a molecule that is used in chemical plants and chemistry labs. We wanted to choose an element that everyone could relate to rather personally, or maybe they know someone that can relate to this element. It is simple enough to demonstrate how to use Avogadro's number, yet still complicated enough to show that we know what we're doing. We wanted to pick something simple enough where it wasn't too hard and we wouldn't be able to solve it, but difficult enough that we could show that we are willing to solve a difficult problem. We thought about using nitrous oxide rather than nitrogen gas, but decided that adding another element would take the focus away from Avogadro's number, which is the entire point of the project. 4.4. The uniqueness of the question discussed. The question is unique because nitrogen gas is simple. Often we see others choose a complicated molecule with more than 4 elements. It is not often we see a simple element chosen. That's why we wanted to choose something simple like nitrogen gas. We didn't add any extra steps since Avogadro's number is the focus of the question. For this question, we believe the simplicity showcases how Avogadro's number is helpful to scientists and students every single day.
So to start with, the symbol for Avogadro's number is Na. N for number, A for Avogadro. Its value is 6.022 times 10 to the 23. And my question is, how many molecules of nitrogen are in 3.0 moles of nitrogen gas? Now, the way we solve this, using Avogadro's number, is first we take the constant, which is, of course, Avogadro's number. It's always the same. And we take the number of moles and the number of particles or molecules present. Now, we know the number of moles is 3.0 of nitrogen gas. And we know the constant. What we're looking for here is the molecules or particles. So to find molecules or particles, we use the number of moles times Avogadro's number. If we were trying to find the moles from using the particles, we would have Avogadro's number dividing the number of particles. So it would look slightly different. So if we take 3.0 moles of N2, nitrogen gas, over 1, and we multiply it by 6.022 times 10 to the 23 over 1 mole of nitrogen, the moles of nitrogen will cancel, and the value that we get when after multiplying the number of moles by Avogadro's number will be our molecules. So I took 3.0 times 6.022 times 10 to the 23, and I multiplied them, and it equaled 1.8066 times 10 to the 24 molecules. Ta-da! And for a bonus,